Hello and welcome back to PC Retro Programmer. In this video I'm going to go through a straightforward implementation of the Midpoint Circle Algorithm in assembly language for CGA Mode 4, the graphics mode. So the algorithm is over on the left here, and it draws a circle with center x0, y0 and radius r. And the radius is measured between the center of pixels, so from the center of x0, y0 to the center of the pixels on the circumference. So even if you have a radius of 0 here, you'll still end up with one point being drawn at x0, y0. Now the algorithm is so similar to the Bresenham algorithm that I recommend watching at least up to the video on horizontalish line drawing, because all of the assembly tricks that we're going to use here are exactly the same as there, and I don't want to go through them again in so much detail. Now there are some differences in the algorithm. This one here, dx and dy, are themselves being modified every iteration of the loop. They're not constants like they were in the line drawing algorithm. Now that doesn't mean that we need additional registers, because dx and dy were already in registers in the line drawing algorithm, even though they were held constant in the loop. Now over there we were using 2dx and 2dy in the loop, and it's only dx and dy here, so we could think about whether we really need 16-bit registers for both of these, but as it turns out we have plenty of registers. And in fact, one of the other major changes here will actually save us a register. So we're using a while loop here instead of a for loop with an iteration counter. So this while loop just does a comparison between two things that are already in registers, and so we don't need an extra register for the iteration counter. So we'll use that extra register that we save for something useful that you'll see in a later video. Now the leading code here is going to be different, of course, because all the starting values are different, but most of the rest of it's going to be the same. One of the things to watch out for is this dy plus 1 here. So it's very tempting to look at this and say, well, if we're going to use dy plus 1 every iteration, why not just make it 1 bigger throughout the whole thing, and then we could just use dy. So we could just increment it outside the loop once and for all, and then we wouldn't have to do this additional plus 1 all the time. Now ordinarily that would actually be a really good idea, but it's not going to work here because we're not actually using dy plus 1 here, we're only using dy. And so this would have to be changed to dy minus 1, and unfortunately that additional subtraction there would really mess up the code for this comparison. So it's the logical thing to do actually is just to add the extra 1 to d every iteration. We don't need to modify dy at all, of course. And so that's just an extra inc instruction every iteration, so not really a big deal. Now the midpoint circle algorithm appears in lots of different forms online. Some of them are even correct. A lot of them have gaps in them at various sizes. They'll work for most sizes of circles, and then there'll be just some of them that don't look right. And the reason that you end up with gaps is because this algorithm only implements one octant of a circle, 1/8 of a circle. We're actually going to have to come up with 8 different versions of this, all just very slightly different, to draw the whole circle. We'll just use the 8-fold symmetry of the circle to derive the other versions from this one. Now once we get the first variant, then all of the others are trivial to get from that. So it's not really a lot of work to do all 8 of these. Now I've actually gone ahead and implemented this algorithm, so let's take a look at that. And I've done this of course in Turbo Assembler, so let's just open that up using the DOS editor here and take a look at how it differs from the line drawing implementation that we already did. Well, you can see that I've called this function CGA Circle, and I've put an extra underscore here. This is force of habit, so when you're interfacing assembly language to a C program, The C compiler adds an additional underscore in front of all its names of functions behind the scenes, and so if you want to interface to C, you have to match that. From the assembler's point of view, there's nothing different here. It's just a function called underscore CGA circle, but C will require that. Now, if we were really doing this as a function to be called from C, then I'd also make the symbol public with a public declaration. But I'm not actually going to be doing any C interfacing here. So, of course, the function takes the three arguments that we expect, x0, y0, and r. And, of course, it'll also take a colour that we're going to draw the circle in, the CGA colour 0, 1, 2, or 3. And the register assignment is going to be identical to what we did for Bresenham's line drawing algorithm. The only difference here is that we don't use CX at all because we don't have a loop counter anymore. So we actually have a spare register. Now, the lead into this code is exactly the same as the line drawing code, so I won't go through that again. And here's the first thing that we do, and that is to make 2 copies of R. So I'm going to save one in the DX register for a bit later in the lead-in code here. We won't touch DX in the meantime. And then there's the second copy of R that we'll put in DI that we're going to use immediately. So we need that because we have to compute the offset and the color and mask for the very first point that's going to be drawn. So this circle is actually going to start drawing from the point on the rightmost extent of the circle in line with the center. So that point is going to have x coordinate x0 plus r, so the center coordinate plus the radius, and the y coordinate will just be the y coordinate of the center line if you like, and that's y0. So we do exactly what we did for the line drawing. We compute the part of the offset corresponding to x first, and that's going to require us to compute x0 plus r on 4, and we'll also need x0 plus r mod 4 for the color and mask. So this first line is just to compute x0 plus r, just a simple addition, and then this is identical to what we had in the line drawing code. And also the color and mask code here is also absolutely identical to the line drawing code, so we don't need to touch on that. Now we want to compute the y component of the offset, and so we load up y0 into AX, and then we can use exactly the same code that we used for the y part of the offset of the first point in the line drawing code. So the first part's obviously to do with whether we have an even or an odd line in the CGA memory, and then we have to multiply y0 on 2 by 80 because there are 80 bytes per line. And so this is identical to what we had in the line drawing code. So now we need to compute d and dx. Now d is supposed to be 1 minus r, and remember that I saved r in dx up at the beginning there. So 1 minus r is just a simple subtraction here, and then dx is supposed to be 2 times r, so I just shift dx left by 1 bit, that'll multiply it by 2, so then dx will have 2r in it. And finally we have to compute dy, and that's supposed to be 0, so we just XOR to get 0. Now the main loop is actually also fairly similar to the line drawing code. The first thing that we do is just draw the pixel at the current location, and everything's already set up for this. We keep that information up to date every iteration of the loop. So this code is the same as the line drawing code, and the next 2 lines are where things are a little bit different. So this is our if statement, and the standard way of doing an if statement is to do a comparison using the CMP instruction here, and then to use a conditional jump. So in this case we have to compare d with 0, so that's what this line is for, d is in SI. And remember that you want to jump over the body of the if statement if the condition doesn't hold. So in this case, if the condition doesn't hold, then d is less than 0. So we need a JL for jump if less than. So that's a standard way of doing things. But in the line drawing code, we had something different. Instead of having a CMP instruction, we were able to omit that entirely. And the reason was because we had an arithmetic operation on the line before, which modified SI. Now, if you have an arithmetic operation which modifies a register, then it's as though the flags are set for a comparison with 0 at the end of the arithmetic operation. It's just a side effect of arithmetic operations. So there's no point in then going on and doing another comparison of SI with 0, because it's kind of automatic at the end of arithmetic operations that happens. What arithmetic operation could we put in here that modifies SI? Well, let's go over to our algorithm and take a look and see what we could put there. So this is where we want to put it. And just looking down here, it looks like this is the most logical line to move up. So instead of doing it at the end of an iteration, we'll do it at the start of the next iteration. So we can just move it up to here. We're not touching D here, we're not touching D here. So it's fine to move it all the way around to here. So this code should be pretty much the same as what we had before. The only problem is the first iteration. On that iteration, we're now messing up D before we do the comparison. So maybe we can compensate that though. We're only doing that on the first iteration, so that's the only time that this wouldn't have otherwise been run at the end of the previous iteration. So what are we doing? We're adding dy plus 1, and on the first iteration dy plus 1 is just 1. So this will just be an inc d normally on the first iteration. So let's compensate for that by decrementing d outside the loop before that first iteration runs. Alright, so we just take 1 off d here, that's easy to do. So now this code should behave exactly the same way. So let's go back to our implementation here and make those exact same changes. So this is where we compute the initial d. So instead of 1 minus r, we want to have r but negate it. So let's negate si here. So now we have minus r, and this one here we want to be 2r, and that's still going to be 2r because r was in dx and we didn't touch it. Alright, and now we need to move our d plus equals dy plus 1 up from the bottom of our loop to here. So let's do that. Where is it exactly? It should be just down here. Yep, that's those two lines. So let's cut those, and we'll go back up to just before that comparison, and we'll paste it in there. Alright, so now we don't need that comparison. The flags are already set as part of this addition here because we modified SI. And as I said, we jump over the body if the condition is not true, so it's JL. It has to be a signed comparison, obviously, because we're comparing with 0. We want to know if it's greater than 0, less than 0, or equal to 0. So that's a signed comparison. So then we do the body of the if statement. Now the first thing is to decrement x, and this is the exact same code that we used in the line drawing code for that. Then we need to subtract 2 from dx. Now we didn't have this in the line drawing code, but it's pretty straightforward anyway. You can just decrement x twice. Now I could have done a subtract here. I could have done sub dx comma 2, but that would actually be 3 bytes of machine code, and I just happen to know that 2 decrements is only 2 bytes of machine code, and on the 8088 it's always going to be faster if you have fewer bytes of machine code, so this will be actually quicker than doing a sub dx comma 2. Do exactly the same thing, but just faster. So then we want a d minus equals dx, which is just a subtraction, and that's the end of our if statement. So finally we need to increment y, and that's the exact same code we used in the line drawing code. We're doing 8113 here instead of 8112 because we need to compensate for the STOSB instruction in our draw pixel. Remember that always increments DI, and we don't want that, so we subtract it back off again by just adding an additional 1 here in this subtraction. Alright, and now finally we have to add 2 to dy, so that's just 2 increments. Again, for the same reason. We could have used an addition here, but this will be slightly quicker. And that's the end of our loop. So we now have to do the comparison for the while loop, and that's just a comparison of dx with dy. So dx with bp in this case. Now we really have to do a comparison here. We're not comparing with 0, so there's no way that we can use the same trick that we did above. It only works when you're comparing with 0. And it's also got to be a signed comparison, but the reason for that's a little bit technical. So let's have a look at our algorithm and see why this has to be a signed comparison. So in the algorithm itself, it's first of all not going to be a problem to put the comparison at the end of the loop instead of the start. The only thing that's going to mess up is the first iteration. But if you think about the first iteration, we're comparing 2r with 0, and 2r is always greater than or equal to 0, so we don't need to do this check on the first iteration. So it's absolutely fine to have the comparison at the end of the loop instead. So that's the first thing. But why does it have to be a signed comparison? Well, think about the case where we start off with dx is 0 because the radius is 0, and dy is 0. In that particular case, what will happen is this if statement will end up being true, and we'll end up having dx minus equals 2 here. So dx will become minus 2, and we'll have dy plus equals 2 here, so dy will become 2. So then when we do the comparison, which should be the final one, it should stop at that point. We'll be comparing minus 2 with 2. And that is a signed comparison because of the minus 2. So if we put an unsigned comparison there, it would just keep going, because minus 2 in 2's complement is a very large positive number if it's unsigned. The same bit pattern corresponds to a very large positive number. So we'd end up with the loop just going over and over well past the end, and so that would be a problem. So it has to be a signed comparison, so that's why it's JGE. But that's the end of the loop and the end of our algorithm, so we just pop our registers in return, and now we're on to the main program to actually drive this function. Now the main driver program barely merits mention. We do almost exactly the same thing as we did for the line drawing. Of course we set the video mode, and then we push all the arguments for our circle function onto the stack. Of course we're calling CGA circle now, not CGA line. And there are only 4 arguments this time instead of 5, so this adjustment to the stack here goes down to 8 bytes instead of 10. And everything else is the same. Wait for a key press, restore the video, and terminate the program. So let's save the changes that we made here, and let's exit, and then we'll actually assemble this. So TASM circle 1, and hopefully we didn't make any errors, and then we'll link it all together, and that should go fast. And finally we can have a look and see whether we got it right. And as you can see, it's drawn about 1/8 of a circle there, which is exactly what we wanted. And so all that's going to be required now is to go in and write versions of this for the other octants.